they used 10 different pairs of garments, or it could be 10. And then they ripped the garment in half and treated half with the solution with treatment, and the other half was washed with cotton oil. And then after washing the two, we measured the size. Okay, and we have some sort of response here. The larger the measurement, the better. Okay. So the effect is mu t minus mu c, right? Just call it delta. That's what we've been calling it. And it's a pair design, so you simply take the differences, and it's a one sample problem. So in this case, I asked for a Wilcoxon, so you would do the sign rank Wilcoxon on the difference. So W would just be the sum of the rank of the absolute difference, right? So we can sum over the positive differences. Okay. And then the null mean is what? There's the average rank is 11 over 2, right? 10 plus 1 over 2, and half of them should be positive. Yeah, I did it right. It doesn't look like I did it right, but it did. It comes out to 27. And then the variance is n times n plus 1 times 2n plus 1. Any questions on that? Because the rest is straightforward. Here's the differences, and then you just take the absolute values and rank them from low to high. There's lots of ties. You just do average ranks, right? It's not new, but it's, you know, it's like third week stuff. Anyways, W turns out to be 32. You expect W to be 27.5. You're on the upside. Is it significant? The variance is 96. So the standard deviation is 9.81. So no, it's not significant. It's not enough, right? P-value is probability Z exceeds 0.41, which is 3/4. So you failed to reject. And then here's the bad part about in-class quizzes. There's no way to do the location estimator. If you did the Walsh averages here, there are there are 55 of them, which is impossible. So I just went to the median. Just use the sign procedure. You estimate delta. That's just the median of the differences, right? Which comes out to be 1 in this case. 90% confidence interval with the C. The cut point is n over 2 minus 1/2, right? And then we want 90%, so it's 1.645, and then it's the square root of n over 4. So that's there. And then that comes out to 1.9. You just round to 2, and then you want the third difference to the 7th, and that's minus 2 to 2. All right, any questions on that? So it's a good review. It's just a one sample problem, right? Any questions on that? Number 2, we're just looking at the independence between first shot and second shot. So 32 times, we got both right. And 7 times. This is, and it's a 2-shot. Yeah, it's not a 1-1. It's just 2 shots. Anyways, there's the observed frequencies, and then there's just row column times. But you just have to do E11, right? It's row total times column total divided by total number. So it comes out to 31.8, and you observe 32, you're almost there, right? But then the margins hold for the expected frequencies too. That's all you need to compute, just the one. And then you can do the others by subtraction. Okay, 31.8, but you have to have 39 altogether. So if you think about it, there's 7.2 left, right? So that's how you calculate that, and then you do the same thing for the row sum, column sum, and then you can go across and go down for the other one. All right, any questions on that? So again, these all have to add up to these margins, even the expected frequencies. So you only have to do one. These things have to add up. Anyways, the difference is only 1.2, you square that, you project. Actually, it comes out to 0.331. So you go with that. Sort of a dumb example of square place. You can't project H0, they may be. Third one is just experiments. You just want to rank the observations from 1 to 7, and then certainly use the shortcut formula that I talked about. Because it's not too bad once you do that. So RS is the sum of the ranks of the x's times the ranks of the y's, right? And then you just subtract off this constant, and then divide by this constant. So if you did that correctly, RS comes out to 2.75. So it's positive correlation, right? At least ordinal. And then the test is just, you can use the t, but I was expecting you to use the z formula. It's just root n minus 1 times s. It comes out to 1. It's a two-sided test, really. So the p-value is twice the probability z exceeds 1.4, which is comes out to 0.66. Oh, there might be some marginal, but it's not significant, 5% null. So we don't have enough information. It could be. Any questions on that one?
So when we're using the t-test, are we actually only assuming the melody there? Is that only going to work with the assumption?
No, that's just an approximation too, and people use it. It's in psychologists I work with here, Brad Hyman, it's in his book. So I started using it a little bit.
So is there any justification for using one or the other?
No, if you look at that T one, I don't have it here. I tried to recall it. TS. Something. Under H naught, this will be close to 0, so it's the same, it's asymptotically correct. I don't mind approximations which are asymptotically correct. In the long run, you're going to be very close to it. The project mostly did very well. I graded them very quickly on the, I do have the answer keys if you wanna look. But I think most of you did it right. I don't, I was written up in Swede, so I could just turn around and do answers. Any questions on that? I don't, it's no use going over it. I think we're going to get this through. It was too long, huh? You might have another one, if you do, you're gonna work in pairs. It's gonna be like 2 answers.
One per person.
Also, there's a real discrepancy on Minitab and our sign rack. So it's something I should look at. I think that's where I saw it.
Mhm.
They really seem to differ. I couldn't believe some of your answers, and I realized you did it with Minitab, and as far as I could tell, you did it right. Like, well, the key was, the t-test was on the money. So that means I thought, well, at least you got the data in correctly, so it wasn't a dumb error like that. So, I don't know, that's probably worth considering. These big packages, I don't think they keep up to date anymore. They just. So it sort of bothers. But before I say anything, I want to go check it out. There was a big discrepancy. It could be ties. Could have been that wrong. Okay, so we use Minitab, so we use the one. And today we're back to Minitab, right? I wanted to go with Minitab. So today what we want to do is actually one way of, but let's review a little bit, because we'll be picking up this test. So I want to go over the test with Minitab. Remember, the problem is this, right? We have a model. I think there are 4 predictors. So we have this model, it's just a regression model, okay? And, no, here's actually the problem, it's this number 43. So these are our 4 predictors. Okay, X1, X2, X3, and X4. And then this is the response log. Okay, well, I can write it on here. Then this would be the full model, right? All the X's are in, so it would be this. Okay, and then for some reason we want to test beta 3 equal beta 4 equal to 0, so we have two constraints. So here we really know the reduced model, it's just this. Right. And then last time we did this in R. Yeah. There's two ways we can go, and it's, we did this one. We did prop test. We fit the full, and then we fit the reduced. And that gave us the drop-in dispersion test, which is just it's the reduction in dispersion. It's D of the reduced minus D of the full divided by the number of constraints. Now there's a second way of doing it, and it's because Minitab does it that way, we have to talk about it. You can write your constraints in terms of a matrix. So in this case, the constraints would be beta 1's not in the hypothesis, beta 2's not in, beta 3 is in, beta 4 is in. Now, if you have that, you can get X reduced and R fit. It's just, it's red for reduced, not. And you have to put the full model design matrix in and this hypothesis. Now, we don't have to do that, okay? We could just do it the way we did last time. But Minitab, this is the way it has to be done. You have to have that hypothesis. Okay? So then, let's do it with Minitab. See, we'll be using this hypothesis test from this point on. We'll be doing other things too, but we'll always have this general linear hypothesis that we can test this with. We can test it two ways in R. You should get the same answer. In Minitab, we can use this hypothesis. Okay. So today, let's look at Minitab. I need the data. Put the data out. Let's see if I can. So there's the data, okay? And I can just copy and paste this. Minitab, the predictor is C1 through C4 for sure. Okay, so, you put the response in C5, I guess. And this one. Okay, so I had the data in, and now I can do a Minitab. And for some reason, we wanted to test this, just do the test, right? So we want to test with that A matrix, so I got to get that matrix into Minitab. But that's easy to do. Just pick like columns 11, it's going to be 4 wide, so like C11 through C14. Just need to read. And then we'll do that just the way I said it. 0, 0, 0, right? 0, 0, 0. And then you just copy that into a matrix. We can print it. So now we have a matrix. Okay? Then the command is, it's our regression, right? We talked about that. And then you put down what the response is, and then a number of predictors, just like the record, and then where they are. Okay, and then the subcommand is hypoth, and then you put down the hypothesis. Then that's the end of the subcommand. Any questions on that? Then you just have to enter, and then it does it for you, and there's the F test, 0.22. Looks like we're not going to reject it small. And it also gives it these squares. Then we repeat them. Just get the critical. I hope someone in this. Period. Set. To it's 4.1, so we're not going to reject. Any questions on it?
So when we're actually doing this, just to make sure the tau cat is coming from the full model, that's the estimate of tau.
Yeah, right. And it's not given to you, it's not a very good command. It's a little bit flaky, it's old. But anyways, I know a lot of you use the Minitab, so this gives us an option. It's like, It's like the most important thing is the option. You have an option.
Do you roll it up? A little like, put it in the bottom?
Yeah, we could do the fix.
I just wanna see how.
It comes out. There's the fit to table coefficients, okay, the score predictor, and it gives you the rank coefficient. I'm assuming it's the standard. It's very poor. I'm not sure. You can check out these squares. The estimates are about the same. We could put a huge change in the model. Typographical error. Actually, if you need to do that, F test change that much, right? Yeah, the fits change. Good, right? Any questions on that? Any questions on mini tab then? Okay, so now we can go, let's do one way and move on, then we'll, we could continue using mini tab. One way I know was just an extension of the two-sample problem, okay, the case samples. In fact, in the old days, I would have called this the case sample problem in this class. That's essentially what we have, and the design would be, it's like a single factor at, single factor A, say, K levels. Or you could have K treatments. Could be observational study. We just have K groups. Or K populations. Okay. And then your data just consists of well, suppose it's a completely randomized design, that would be design with this. So in this case, you have K different things you're looking at, K treatments, right? Or K levels of the factor A, and then you randomly select N items or N experimental units from your reference population, and then you randomly assign N1 to treatment 1, right? So name select and experimental units. And random 1 to 3.1, right, or level 1. And then K to 3.4. That would be the design, then you would have a test period. And, at the end of that period of time, then you would collect your data. Then you just have K samples. So that would be the design, but it could just be an observational study. You just have K groups, and then you collect a sample from each group. Okay? If it's a CRD and you keep all the other variables, which could have an effect on response in control, as much as possible, then you can start talking about cause and effect. Otherwise, you can talk about likelihood association, so there's a difference in groups. There seems to be a difference in populations. So the data could be design or it could be an observation. So the computer data. Well, you can model the data this way, just like YIJ, the ith response. No. Now it's J. So I would go from 1 to K, right? And then J would go from 1 to S. And we had N be this total sample size. Now the most powerful design will be balanced. All the N sub i's will be the same. Usually you start that way. Why would you do something different? You'd have to have a reason, right? Because it is the most powerful design. But then something happens, animals die, or whatever. So you may end up with an analysis. Then we'll be just looking at location models. So model this as location, right? In the following way, that's our basic model. Okay. Now what's of interest here, definitely, here's the effects, right? It's not the means for the most part, it's the difference in means, right? We might even use a delta notation. So those would be the effects, right? There are actually, they choose two effects. You probably have an overall hypothesis that the levels do not matter, okay? All the means are the same. Notice you can write these in terms of constraints. There's only K minus 1. So if you want to, you can use that delta notation. Notice I referenced the first one here, so it's delta 1. Really exponential it is. You don't have to pick on the first one. So it's really just K minus 1 constraints. So that's the hypotheses of interest, and it's, you know, we just generalized the two sample problem. For the two sample problem, we just have one effect really. We didn't use delta 1, 2, we just called it delta. So we could have done it. Okay, now it's just larger, right? And then probably after these, right? You want to estimate those, and then you want the confidence interval. You can guess most of it, right? It's going to be, there'll be a standard error of some sort. Tau hat or sigma hat, and then, but you know the rest. It's just this. It's done. You can't. It'd be horrible if you just didn't generalize the way you had.
Is you,
Yes.
some simple question on notation. Is that I dot for your delta hat? Or is it IJ dot?
It's I prime.
Oh.
Sorry. Wait, looks like I wrote the effect to 0. It's here now. That has no effect in this one. 0. Let's see how did that. Okay. Is it clear what we have to do then? The problem is to test that hypothesis and then do maybe multiple comparison procedure or whatever, estimate the effects. That is this is like the new wrinkle. Right? You have K choose 2, but often you don't have that. For instance, often like the first guy, the first level is SIBO or control, and then you're just looking at, you just have K minus 1 effects. And sometimes the problem is not as complicated. Okay.
These three. N minus 1, right?
Okay, so let's look at an example. I'd like to and we could pass ahead. I often do this. Supercars. I've got some data. I've got supercars, all right? Supercars. Okay, we have data on an Acura, a Ferrari, a Lotus, Porsche, and a Viper. So we're going to solve the Westminster problem. How can I get from A to B on Westminster? So we have these are actual runs. The top speed achieved using as much distance as needed. The engines cannot exceed, the car cannot exceed the engine's rate. So we did 6 runs, 3 in each direction. So we set some so we have Now, what's the best way to have the data in this case? What you want are the responses, right? And then level or the group indicator. That's really how you want your data because you can do much more with that. Just adding this to the box. Before we get to that, let's think about what we want to do. So this is a data. It's diagnostic comparison box plots, of course. Dot plots. This would really be better, probably dot plots. But we could do the box plots, we just don't have that much data. We have some calculations. So the box plot, you gotta go look at it. Do Q plots. Based on position. So you fit the model. And two, you might fit the model. Get the Z ones right. Then we could do usual diagnostic plots. Then once we're satisfied with the model, then we can go ahead and test the hypothesis. Do the multiple comparisons. Okay. This would be multiple comparison. Any questions on the schematic then? This is what we want to do for this problem. So for our data, so for the supercars, we have 5 for the Acura, Ferrari, Lotus, Porsche, White, YIJ is the maximum speed. This is I. And the J, that's a balanced design, the J goes from 1 to 6. Okay, so then our N is 30. Now, is it actually? It's a it is a design experiment. They were done at the same time, or very close to the same time. They go like up and then back, so they cancel out the wind. Although, if you're a statistician, you'd say, "Well, I want to do some blocking here." It's I don't have it. We don't have it. I'm not sure what was up. Okay, so I just read the data in. Doesn't matter where we put it, I guess. We'll put the response, I guess, in CV. Okay, so there's the speeds. Okay, and I guess my focus is not gonna be able to keep up. 74 miles an hour. So, 75. Okay, my focus starts to shake it here. And then let's do the box class. This is what we're doing. So we do it. So we want to do, we could do a dot plot, but let's do box plots. Just keep in mind, it might be messy with the let's face it. We do have a grouping like that. Let's hope that's what we do. Yeah, the graph variable is C1. Categorical is let's kill that problem. We're down to a heat race. It's the Ferrari and the Porsche. This is what we need for Westman, the others can regulate it to Oakland or something. It's kind of clear. There aren't any outliers as far as I can tell. Again, there's only 6 observations, so you do have to be careful. And there's just not enough information to say you have a much different variance. I meant to say that, and that's one reason for doing box plots. Certainly if you have enough data, because we are assuming the scales are the same. But again, there's just not enough information to tell this to the court. I'm not sure what this means. Maybe it's this. Yeah, this is trying to see. Yeah, there's dot plots. Again, it's the Ferrari, right? They're reported. So the first, let's do a non-parametric test first. It's just the analog of the Mann-Whitney-Wilcoxon. It's the same thing, all right? You just combine the data and rank them from low to high, and then you look at the sum of the ranks over each sample. And you compare that with the average rank, and if there's a large discrepancy, it's not. The goal is to get it to one statistic. But it's really straightforward, just boils down to that. So let's do that test first. This is called the Kruskal-Wallis test. Okay. And you should always think of a schematic in your mind when you're doing these problems so you don't get lost. And the schematic is you do have 5 samples, and we'll just write them down like we would the old days. Right? or at least think of it. So you have what sample, in this case, we have 5 samples. We could just do a general. This would be the ith one, right? And then we're out to k. And then this would be yij is right. So that's the schematic. That's what's going on. That's our data. And then we just combine these and rank them. So we could just leave them like that with their ranks. So it's Rij, it's just the rank of Yij. Ties the same way, average ranks, right? I, the average ranks, one over n is 5, some j. So each of these, this will be R bar 1, R bar 2, R bar I, R bar k. So that's the average rank. Okay, now we've taken the average, and then we could compare this with the average rank, which would be n plus 1 over 2, right? Then it doesn't matter if it's negative or positive, it's a discrepancy. So I take absolute values, which we're not allowed to. We use squares. So it takes care of that. And then someone tells you, well, the first sample size is 10 and the second sample size is 80. You say, well, that 80 has more information, so you have to weight that accordingly. That's it, except you have a standardized constant. This is called H, usually. And that's the crust of walls. That's all there is to it. And you inject H1. Well, H exceeds chi-squared critical point. A minus 1. Now H is distribution free, okay, and for small samples there are tables. But we'll just use the chi-squared flux. Okay, any questions? It's just an extension of the Mann-Whitney. If you had 2 samples, put it through H, you'll come out with the Mann-Whitney square. The standardized Mann-Whitney Z. Okay? If you square that, you'll get the chi-squared value. So in that sense, it's not new. So then how do you compute it? If you're on R, it's Kruskal.test. So Y. So we're collecting the Yij. This would be what I'll call it. If you're on many tabs, this Kruskal, C1, C2, like we. a moment. So we did a box plot. It looks okay, so we'll just do, it's just crustal C1s. Yeah, 22.4. Nice. 0 to 3 places. Yeah, so 5% value. You could use the p-values. But it's just going to be 0 to 6 places. Any questions on that? So you would reject H naught here. And that would say, going back to this. Well, then I should have had A down, probably didn't. What is HA? It's just, in a sense, it's not H naught. You know, H naught would be the means are the same, right? And the alternative is these two. So for the car data, reject H naught. And certainly include these two cars. Okay. Any questions on that? Well, let's start thinking about the multiple comparison problem then. And we have to decide what we want to do with this. You can do individual man Whitneys. I don't like to do it that way. I like to fit an overall model. That's probably what I'll do. Next time we can think about that. Probably want to do something, okay? There are people who believe that you collect a lot of data and test one hypothesis and then you're done with it. That's not the case, right? You want to go and you want to look at this. You've got to decide whether you should buy a Ferrari or a Porsche, right? That's the important question for Weston. Those we can throw away, and hopefully the multiple comparison procedures come up with will say that, and then hopefully it was the Ferrari was a little bit ahead, but is that significant? Certainly you would hope that overall hypotheses would be rejected, right? That's really stark. You don't even need statistics for that. But now when you try to pull apart Ferrari and Porsche, you only have 6 data points in this sample. So there's a discrepancy, a difference there. It's real. So that's what we have to do. So that's, we're down to those. Did we talk about the bond parameter? We talked about the bond parameter. The problem you have is you have an overall, you'll have an overall slippage in confidence. Right? You're gonna have to do a lot of comparisons. This one isn't too bad. It's 5 choose 2 on the drawing. There are 10 comparisons in that table in part A. So, if you were up to 20, then there could be nothing going on. You'd expect to ring the bell once, 5%, 1 out of 20. So you need some way to compare. And we'll talk about at least 3 ways. The first way is based on the test. I'm going to do the usual confidence intervals. All right, that's Fisher's way. The second way is. The second and third ways are almost equivalent most of the time. Bond parameter. So we'll talk about that next time. And we'll have to talk about it. Okay, so there won't be a quiz. There might be a quiz a week from today. Okay, we'll talk about that. Maybe last week. Okay, so we'll finish this next time. I don't think left is one.